Infrared spectroscopy is a technique that characterizes vibrational transitions in organic molecules. In terms of the region, the IR region of the spectrum which we deem useful for this kind of spectroscopy, this region is between 2.5 times 10 to the minus 6 meters and 2.5 times 10 to the minus 50 meters. In other words, between 2,500 and 25,000 nanometers. Okay. For comparison, the visible region of NMR electromagnetic spectrum is between 300 and 700 nanometers. Okay. Now, IR spectroscopy, although we could express all IR vibrations in terms of their frequencies or energies or lambda, for traditional reasons, IR spectroscopy uses a unit which is known as wave number, which is defined as this mu letter with a dash. And this number is nothing other than the reciprocal value of lambda, of wavelength. And so hence it's expressed in meters to the minus first, but more commonly, and especially when we're dealing with IR spectra, it's expressed in centimeters to the minus first. Okay? Now, while energy is inversely proportional to lambda, the higher your lambda, the lower your energy, it's directly proportional to the wave number. So the higher the wave number, the higher the energy. Okay? And so then the IR spectrum region transforms into 400 to 4,000 centimeters to the minus first. And this is what you'll often see pretty much in all IR spectra that you'll see in this slide. Okay? Now, IR light, although it is very close in energy to the visible light, is quite different. And there are materials that that appear very non-absorbing in visible spectrum, such as water, which is transparent, or snow, which is white, or glass. But all of them are very strongly absorbing in the IR spectrum, and they basically look black under IR light because they absorb all IR light. And so things like water, snow, or glass, they all absorb IR light strongly. Now, one of the things that causes a problem here is glass, because IR is a spectroscopic technique, so it basically deals with light. And so if it deals with light, then you need to have some sort of lenses and some sort of optical elements, which are, in our normal routine life, they're always made of glass. And if you can't use glass, then the question is, well, what do we use? And so IR optics is not made out of glass. It's made out of finely polished surfaces made from sodium chloride or potassium bromide or silver fluoride or something like that. And what you'll notice about sodium chloride and potassium bromide is these are salts. And not only that, they're salts that are soluble in water, which means that IR spectrometers as instruments are very sensitive to moisture because their optics basically dissolves in water, and so they need to be kept under very highly controlled low moisture conditions. Okay. Okay. So now with all this out of the way, let's see what does IR light actually do to a molecule. So if we have a molecule, then that molecule will have one or more excited electronic levels, and to transition between these two levels we need a lot of energy. And so this will be the UV light, because this will be an electronic transition. However, within each electronic level there are multiple small vibrational levels, and the energy between them is much smaller, and so this will be a vibrational transition. And this is what IR light does. It excites molecule from one vibrational level to a higher vibrational level. Okay, so and the energy of this delta E equals h nu, and so this is the frequency, or it's also hc over lambda, or hc wave number. And this means that this energy that is needed to transition between these two levels would correspond with frequency, or lambda, of the IR light. And if the energy tells us anything about the molecule, that means that by using a light of appropriate frequency, we'll be able to confirm whether that parameter of the molecule is present or absent. Okay? And so this energy is really molecule signature in a way, because it tells us what is there that's vibrating at that specific location. A lot of IR spectroscopy can actually be explained in terms of very simple analogy with a spring, because this is the vibrational spectroscopy and springs vibrate. And if we have two spheres attached to the ends of the spring, they can correspond to atoms attached to the ends of the chemical bond. And the so-called Hooke's law, which was defined for not for IR spectroscopy, but instead for normal mechanical vibrations, tells us that this wave number will be proportional to a certain constant and square root over k over mu. K is proportional to the bond strength. And while mu is a much simpler thing to understand, because mu is basically m1 times m2 over m1 plus m2, and it's a so-called reduced mass. Okay? Now, from this reduced mass concept, we'll notice that the lower the mu is, the higher this parameter will be, the higher the energy. Okay, so if we have lighter atoms attached to a bond, then we'll need higher energy or higher wave numbers to excite them to vibrate. So if we compare the wave number for CH vibration, which is two light atoms, it's about 3,000 reciprocal centimeters. This is greater than the vibration of a CC light, which is about 1,200 times. Equally, and this is actually quite diagnostic, that we can use CH, that will be greater than C deuterium, because deuterium is heavier than it, and this is about 2,100 centimeters. Another parameter that comes out of here, that the stronger your bond, you will need more energy, and that is pretty straightforward. So if we have stronger bonds, then you will require higher energy to stretch them or bend them. And so if we have the frequency of the CO double bond vibration will be, of course, greater than the frequency of CO single bond vibration. The corresponding numbers will be 1,700 and about 1,200 reciprocal centimeters. Okay? In the next subtopic, we will see how a typical IR spectrum looks like, but we'll finish this subtopic by stating one important fact, and that is that completely symmetric vibrations cannot be observed in IR spectra. The reason for that is the IR spectra basically measure the change in the dipole moment that occurs during the vibration. If your bond is completely symmetric, then there is no dipole moment to it, and if you stretch it symmetrically, then you still will not introduce any dipole moment to it. So if we have a bond such as this alkyne triple bond, which is completely symmetric in this 2-butene, we will not be able to see that vibration in the IR spectrum. So that's something that you always need to be mindful of, even if you have certain functional group, but it's substituted in a completely symmetrical fashion. It will either be weakened or it can completely disappear from your spectrum. Now, in the final subsection of this lecture, we will see how do we interpret IR spectra. We will look at some actual experimental IR spectra and try to identify functional groups present in them, and then we'll finish our treatment of IR spectroscopy.